Good afternoon, morning, evening, or whatever time you are watching this. Hope you guys are having a good day. Today is our video for Friday, and I've got a special video for you today. We've already talked about energy applications for a lot of different power sources. We talked about hydroelectric dams, we talked about wind turbines, we talked about solar panels, and today I wanted to talk to you about a new or a different kind of new to you and a different kind of um, way to harness electricity, which is with a nuclear reactor. The kind of reactor that I wanted to talk to you guys about today is one called a boiling water reactor. And the reason that they call it a boiling water reactor is basically in the name. It's a boiling water reactor because water boils inside of the reactor core. So water boils inside the core. Um, most of the nuclear power plants that we have in the United States are actually not boiling water reactors. They're a different kind. There's advantages and disadvantages to using boiling water versus a different type. The reason I wanted to talk about boiling water reactors is that they're a little bit easier and more simple to draw out and talk about, and that's because they run on one loop versus the other kind of reactor runs on two separate loops. So you have a lot more kind of going on with the other kind of the other kind of reactors that we use. So today I want to talk to you guys about boiling water reactors, how these reactors are the thermodynamics and the cycle involved with producing electricity from a boiling water reactor. And probably the place to start with your boiling water reactor is with your reactor core. So every power plant has some source of the actual energy, some place where the energy comes from. In the case of a boiling water reactor, that energy comes from the reactor core. Heat is produced in the reactor core, and that's because inside of the reactor core, there's a very powerful process that's going on to produce that heat, and that's called nuclear fission. So nuclear fission occurs inside of the reactor core, and that's the process by which nuclei or atoms are broken apart. And depending on what the atom is, if you break it apart, you can actually produce energy from that, and you can create a self-sustaining chain reaction that causes the production of this power to continue on in a very controllable kind of way. So basically, you have this nuclear process that's happening inside of this reactor core, and it's producing a lot of heat. An insane and incredible amount of heat is being produced in this reactor core. And if you don't have some way to control that heat, this reactor core will very quickly start to melt down. It will heat up to a certain point where everything in it just begins to become like molten lava melted junk. So to keep the reactor cold, or at least to keep it at a temperature where it doesn't melt down, what you have to do is you have to send a fluid or some kind of something into your reactor core to keep it cool. And the thing that we use in our reactors is the thing that we keep our reactors cool with is just regular water. We have cold water that goes into the bottom of your reactor core. That cold water runs over the nuclear fuel, and as that water runs over the nuclear fuel, because the nuclear fuel is very hot and the water is cold, thermal energy gets transferred from the reactor core into the water. So basically, inside of the reactor core, you have a heat transfer from the core to the water, and that causes the water to be heated. It causes heating. Eventually, that water heats up to the point where it begins to boil. And when water starts to boil, it produces steam. So, really, once the water starts boiling, you produce steam. So, you heat, you boil, and you produce steam. And so that's what comes out of the top of the reactor core. What comes out of the top of the reactor core is this very hot, superheated steam. So you have basically very hot steam. And whenever we talk about steam, that's just water vapor. Very hot water vapor is coming, water in its gaseous phase is coming out of the top of the reactor core. And that, what you do next is this is you get the electricity from your power plant. It comes from this steam, because what you do with the steam is you make that steam go into a turbine, just like very similar to with your hydroelectric power plant. You have that flowing water that turns the turbine. Well, you can also make a turbine turn with by pushing very hot steam through it. So by running this hot steam through the turbine spins. The spinning of that turbine produces mechanical energy. So basically you get mechanical energy out of your turbine. That mechanical energy goes into a generator. That generator, the rotation of that generator causes a current to be produced through induction, and that's how you get your electrical energy out of your reactor. Positive and your negative, and that's your electrical energy coming out of your reactor. So this process right here, you've seen this a lot, right? You guys saw this with the wind turbine. You saw this with the hydroelectric power plant. Pretty much this kind of process where you've got your turbine and your generator producing, going from some kinetic energy or some thermal energy to some mechanical energy to some electrical energy. This is a very common process. Very almost all of the power that we produce in every country in the world comes from this. This kind of process right here happens all the time. Almost all of the electricity that we're producing has this going on in it. And if you take more like physics classes or thermodynamics classes and engineering, then you can learn a lot more about what's going on in all of these different um, in these different components, and you can learn how to better engineer them, how to improve them, and you can get a job, hopefully, designing these things, making them better, working on them, learning about them in more detail, and things like that. So yeah, basically, so that you have this hot steam goes into the turbine, you have a conversion of the kinetic energy of the steam into mechanical energy, but the steam, once it goes to the turbine, it's actually still steam. So basically, what exits the turbine is still steam, but you basically have taken away its energy. So you can basically think of this, you can basically think of what's coming out of this as being low pressure steam. Taking away its kinetic energy in the turbine. Oh yeah, and by the way, just so we're clear, inside of the turbine, what's happening is that you're converting the kinetic energy of the steam that's being converted into the mechanical energy of the turbine blades. Just like with the wind turbine or with the hydroelectric power plant, you have some fluid that's turning your turbine. In this case, it's just steam that's making the turbine move versus water making the turbine move with our hydroelectric power plant, or air making the turbine move in the case of our wind turbine. That energy gets taken out. Now your steam has less energy than it had, so it's basically a steam with a low pressure. And you don't want steam to go into your reactor core in the bottom, because steam is not very good at conducting heat. And that's what you really want to do. You want this heat to be transferred from your core into your water. So once the steam comes, once you have this low pressure steam, you need some way to turn that steam back into water. And that's exactly where our that's where our steam goes next. It goes into a device that does just that. This device is called a condenser, and what this condenser does is gas comes in at the top, and then this device works to condense that. You've got this water vapor, and it condenses that vapor back into a liquid. So this is your condenser. And your condenser is basically just going to cool the steam to bring it back to water, condensing it back, oop, condensing it into water. And so water is coming out. You got your cold water coming out. You might think that this process is ending, and you're pretty much right. But what you want to think about is that these reactor cores are very large to get to move this to these reactor cores, they're about, well, depending on the model, they can be anywhere from like they can be like up to 10 feet tall. So getting all of the water up this reactor, and they're also very wide. So getting the water through this reactor, the water has to have a good amount of kinetic energy or pressure just to make it up to the top and then through this cycle. And so to get that water going through this cycle, basically what you have is a little pump. You have a little pump here, and what that pump does is it just gives the water a little bit of extra kinetic energy so that it can make its journey through this cycle. The water is basically being pumped through and then back, through and back. So you can imagine that every single time the water is right here, it's cold water with a certain amount of pressure that was given to it by the pump. And that's kind of what we mean by this water being in a thermodynamic cycle, that the water is always going to return back to this point. So for the water, there's actually no change in its internal energy as the water goes through this thing, because every time the water reaches back to this point, it's at the same kind of state that it was at. It's cold water at the same pressure that it was um, once it started here. It made its way back to the exact same point with the exact same conditions. So that's kind of what we mean by it being in a cycle with the change of internal energy being zero. Um, and so that's, oh yeah, I just wanted to make sure we were clear about the pump. What the pump does is the pump basically just adds pressure to the system. It adds pressure. It gives the water enough kinetic energy to get through here. It gives it sufficient kinetic energy to make it through this cycle. That's basically what our pump is doing, forcing all of this water to go through your reactor core. So people have talked about boiling water. Well, they've talked about nuclear reactors in general as the most expensive and complicated way to boil water. And now you're kind of getting a idea about why people might say that, right? This is all happening because you have a nuclear reaction causing basically steam to turn a turbine to produce power. This is what's going on here is no different than what happens in a coal power plant or a gas power plant for that matter. The only difference between a nuclear power plant and like a coal or gas plant is the source of electricity. I could cover this reactor core up and I could put coal generator or I could put natural gas generator, and this picture would look the exact same for a coal power plant, for a gas plant. The only difference is that your heat source is from nuclear reactions versus chemical reactions of combusting your coal or your natural gas. And just to give you a scale about the energy produced from these reactors, there's a power plant in Texas, in South Texas, called the South Texas Project, or STP. That's the big nuclear power plant in Texas, and they're planning on building two boiling water reactors that have a electric power rating of 350 megawatts. So if you think back to those big, incredible wind turbines that we were talking about, those offshore wind turbines, they were producing about 8 megawatts. So one nuclear reactor is equivalent to about 170 of those. If you do 1350 divided by 8, you get about 170. So that means that one nuclear reactor, one of these boiling water reactors, is producing the same power as 170 of those giant offshore wind turbines that were like on the scale of like buildings, skyscrapers, and things like that. So just to give you an idea about the scale of the energy of these power plants, 1350 megawatts, that's 130 or yeah, that's I haven't done the conversion in my head, so I don't wanna get it wrong, or haven't done the conversion on paper, and I don't wanna do it in my head and get it wrong, but that's an incredible amount of power. That's way, way more than was being produced even by those giant wind turbines, and it's pretty much the largest source of power that we've got in terms of producing a lot of power in one place. So that's one reason why people are very interested in nuclear power, is that it's a way to produce a incredible amount of electricity. The other benefit of nuclear power is that even though this process does produce waste, the nuclear fuel is a waste product in the end. You don't get to use all of it, and once you're done with it, you have to store that waste. This process does not, however, produce CO2 in the generation of this. Nothing is being burned, and nothing is being released into the atmosphere except for heat and steam. So that's a benefit of nuclear power in that it doesn't contribute to climate change uh, in the ways that conventional power plants do, like coal and gas. So hopefully that gives you a better understanding about how these power plants work, gives you an idea about the scale of the electricity that's produced by these guys, and is kind of giving you the picture of what you would see if you were looking at the details of these plants and what's going on inside them to actually make electricity. So, hope you found that interesting. If you guys have any more questions about this or anything else that we've talked about, feel free to reach out. Thank you for your time. Good luck on your questions, and hope you guys are having a great day and have a good weekend. Take care.